Hi all, welcome back to Computer Organization course. We'll get started. Today we will get started with the chapter 4, that is Input Output Organization, and here is your marks split up. In this chapter we will learn how programmed control IO is performed using polling, the idea of interrupts, direct memory access, data transfer over the synchronous and asynchronous bus, the design of IO interface circuits, and then lastly the commercial bus standards, particularly PCI, SCSI, and USB. Okay, first we'll have the intro. So, one of the basic features of the computer is the ability to exchange the information with the other devices. Now, this communication enables a human operator, for example, a keyboard and a display screen, to process text and graphics. So, we make extensive use of the computers to communicate with other computers over the internet and access around information around the globe. So, in this chapter, we will consider the detail various ways in which the IO operations, input output operations, are performed. Okay. So first we will consider the problem of from the point of view of the programmer. Then we will discuss some of the hardware details associated with the buses and IO interfaces, and then introduce some commonly used bus standards. First, we will see how can we access the IO devices. We had seen this similar picture in the chapter 1. This is a single bus architecture wherein your processor, memory, and IO devices are connected to a single bus. Now this bus is a external bus. Okay, so this is external to your processor. Okay, this is a system bus. Remember this one. Now for this bus, we have processor and memory connected, and we have n number of IO devices can be connected. Now this bus enables the single bus, it enables all the devices connected to it to exchange the information. So now this bus, what it contains? So this bus contains three sets of line. One is your address line, the second one is data line, and the third one is control lines or control signals. Now we can have n number of IO devices here, right? Each IO devices will be assigned a unique set of address. So when a processor places the particular address on this address line of this bus, the device, it recognizes itself and it responds to the commands issued by the processor on the control lines. Getting it? The processor either requests a read operation or a write operation, and the requested data are transferred over the data lines to the processor. Now, whenever this IO device and the memory, if they share the same address space, we call that arrangement as memory mapped IO. With this memory mapped IO, any machine instruction that can access a memory can be used to transfer data to the IO device or from the IO device. For example, if data in is the address of the input buffer associated with the keyboard, the instruction, this, okay, we have discussed this one. So okay, this instruction, okay, the move data in comma R0, what will it do? From the data in register, the content would be moved to processor register R0. Similarly, move R0 comma data out, what it does is the contents of the R0 would be moved to the display. Hope you guys remember the data in and data out, these registers, buffer registers, which are placed inside the input device and the output device. We had seen this in second chapter. Okay. So most computer systems, they use this memory mapped IO. Some processors have a special in and out instruction to perform IO transfers. For example, processors in the Intel family, they have a special IO instruction and a separate 16-bit address space for IO devices. So when building a computer system based on these processors, the designer has the option of connecting the IO device to a special IO address space or simply to the memory address space. Now, usually what will happen is the IO devices would be connected to the memory address space. This leads to a simpler software. So one advantage of a separate IO address space is that the IO devices deal with the fewer address lines Again, IO address space does not necessarily mean that the IO address lines are physically separate from the memory address lines. A special signal on the bus, it will indicate that the requested read or write transfer is an IO operation. So whenever this signal is asserted, the memory unit ignores the requested transfer. The IO devices, they'll examine the low order bits of the address bus to determine whether they should respond. Next, we will study about the IO interface of an input device. That means we have this IO interface. This is a hardware that will connect the input device to that of the bus. Now, this IO interface, this hardware, it consists of address decoder, control circuits, data and status registers. Now, address decoder, what it will do is it enables the device to recognize its address when the address appears on the address lines. That means whenever the process sends some address line over the bus, when the processor sends some address over the address line of this bus, each and every input or output device will have a unique address, right? So this address decoder helps in identifying the address. Then we have control circuits. So whenever we have a read or write operation, that would be done, that would be sensed using this control circuits. Then we have data and status registers. Input device will have the buffer register called as data in and the status register called sin. Okay. This data and status register of this IO interface, it is connected to the data lines of the bus. Then control circuit is connected to the control lines of the bus. Address decoder is connected to the address lines of the bus. Okay. Now these three together we call them as IO interface. That is the hardware of the IO interface. IO devices operate at a speed that vastly different from the processor. So when a human operator is entering a character at a keyboard, at the same time the processor is capable of executing millions of instructions between the successive character entries. That means, say suppose you are typing your name. Okay, so in between the successive characters, your processor is capable of executing millions of instructions. So an instruction that reads a character from the keyboard should be executed only when the character is available in the input buffer of the keyboard interface. Input buffer is nothing but your data in register. Also, we must make sure that the input character is read only once. Okay. For an input device such as keyboard, the status flag sin. You remember that one, right? So in the second chapter we had seen the last topic. So we would have, if suppose this is a input device, we would have a register called as data in and a status flag called as sin. Okay, so whenever we take an example of a keyboard, so the status flag sin is included in the interface circuit as part of the status register. This one, whenever this flag is set to 1, your processor will understand that some character is present in the data in register and it reads out. So when it reads out, this sin flag would be cleared to 0. So hence by checking the sin flag, your software or the processor, it can ensure that it's always reading a valid data. Now this is often accomplished by a program loop that repeatedly reads the status register and checks in the state of sin. Whenever sin becomes equal to 1, the program reads the input data register. Now a similar procedure is used to control the output operations using the output status flag sout and the register we call that as data out. Okay. Now to review these basic concepts, we will consider a simple example of input-output operation involving a keyboard and a display device in the computer system. There would be 4 registers that would be associated in the data transfer operations, and those are shown in this diagram. The status register, this one, okay. The status register, it contains 2 control flags. One is sin and sout. These are bits, remember, okay. So either it would be set to 1 or 0, and the same for S out, it would be set to 1 or 0. Now this KIRQ and DIRQ, these are used for interrupts. IRQ is for interrupts. So K means keyboard interrupt, D means display interrupt. Okay. Now, okay. Yeah, these are for interrupts. Then we have control register. So this control register again for keyboard and display. We will see this in the later sessions. Then we have data in register and data out register. So this data in is a buffer register for your input device, and data out is for your output device. So whenever there is a transfer between the input and the output, these all things come into picture. Okay. Now let's consider a program that reads a line from the keyboard, stores it in the memory buffer, and displays it on the screen. Okay. Now this program starts with this one, hash line comma R0. So what it means is the program reads a line of character from the keyboard and stores it in a memory starting at a location line. Okay. Now then this calls a subroutine, this process. This process is a subroutine to process the input line. As each character is read, it is echoed back to the display. So we have register R0, which is used as a pointer to the memory buffer area. The contents of the R0 are updated using the auto increment mode so that the successive characters are stored in successive memory locations. Now each character, when it is read, it is checked to see if it is a carriage written character, that is the ASCII code is 0D, okay, this one, or if it is a line feed, that is the ASCII character OA or 0A. So is sent to move the cursor from one line down on the display, and the subroutine process is called. Otherwise, the program loops back to the wait for another character to be read from the keyboard. This program, it illustrates the program control IO, in which the processor repeatedly checks the status flag to achieve the required synchronization between the processor and the IO device. Now this process, we call it as polling. Okay. The process in which your processor continuously checks the status flag is called as polling. So there are two commonly used mechanisms for implementing this IO operations. One is interrupt and the other one is direct memory access. So in case of the interrupt, the synchronization is achieved by having the IO device. It would send a special signal over the bus whenever it is ready for data transfer operation. In case of direct memory access, a separate technique is used for high-speed I/O devices. It involves having the device interface transfer data directly to or from the memory without continuous involvement of the processor. Getting it? Now we have a quiz. So the question is, the process where the processor constantly checks the status flags is called as dash. You have 2 minutes of time. Okay, time up. Next, we will see about the interrupt. Now, what is an interrupt? Say for example, consider a person is talking on the phone continuously. Okay, person A is talking continuously on the phone. Now, say suppose person B comes and he stops him in between. That means person B has interrupted person 1. Now, interrupt is nothing but stopping one from doing his work. Okay. Now, in the last example, wherein we had seen a program where it would read a line of text from the keyboard and display it to the screen. So there, what would happen is the processor, it would continuously check the status flag of that particular device, that is the keyboard. Now, what would happen there is the program, it enters a wait loop that is repeatedly checking the device status. Now, during this period, your processor is not actually doing any useful work. Okay, so there are many situations where other tasks can be performed while waiting for an input device or the output device to become ready. Now, to allow this happen, we can arrange for the IO device to alert the processor when it becomes ready. That means whenever the input or the output device it becomes ready, it has to inform the processor. So what it can do, it can eliminate the processor work of continuously checking the status flag of that particular IO device. It can do so by sending the hardware signal called as interrupt to the processor. Now, how a input or the output device can inform the processor that it is ready by sending an interrupt. So, at least one of the bus control lines called as interrupt request line is usually dedicated for this purpose. Since the processor is no longer required to continuously check the status of the external device, so the same waiting period the processor can use for computing the useful functions. So, by using interrupts, such waiting periods can be eliminated. Getting it? Now, we will consider a task. I mean, to get the knowledge of interrupt, we will consider a task that requires some computations to be performed, and the results of the computation should be printed on the line printer. This is followed by more computations and output and so on. So that the program, it contains two routine. One is compute routine, another one is print routine. Now this compute routine, it will compute something and it produces output and lines of output. Now, so whenever this compute routine, it produces some output. Now this print routine, it has to take that and outputs from this compute routine and it has to print it on the printer. Okay, now this required task, this may be performed by repeatedly executing first the compute routine and then the print routine. That means first we'll compute all the things, all the computations, will get n number of lines and then we will print it. This is one way. Now, but what was our condition? We have a line printer. That means printer accepts only one line of text at a time. Hence, the print routine must send only one line of text for the printing and then it must wait. Again, once the printer has completed, printing one line of text, this print routine has to send the second line of output to the printer. It has to wait till the printer finishes and so on. The disadvantage of this approach, this is a simple approach, but its disadvantage is your processor, it spends considerable amount of time waiting for the printer to become ready. It is possible to overlap the printing and the computation so that you to execute this compute routine while printing is in progress, a fast overall speed of the execution will result. That means, so if we do it one by one, like first we compute, then we print, then but our printer takes only one line of text, is it? So what will happen is your processor has to wait unless and until your printer becomes ready. When it is ready, then it has to send the second line of text. So instead of that, what we can do, we can overlap the process. That is, you can do computation as well as printing is in progress. So if you overlap the thing, what will happen? Overall speed would be increased. Now, how can we achieve this one? First, the compute routine is executed. Okay, this compute routine, it would be executed and it would produce, say suppose entire compute this routine, it will produce say some 10 output lines. Okay, now first whenever we are trying to overlap, what we can do is, say suppose this compute routine is executed and it produced 5 output lines, 5 result it has produced. Now what can be done is, the print routine is executed to send the first line of text to the printer. At this point, instead of waiting for the line to be printed, your print routine can be temporarily suspended so that the execution of the compute routine can be continued. That means overall we had 10 output lines. Say suppose 5, your compute routine has performed computation and it has produced 5 lines. So what can be done is, these 5 lines can be sent to the print routine and your print routine would be sending 1 line to the printer. Now your print routine need not wait till your printer has printed the first line. What can be done? Your print routine can be suspended once the line of text has been given to your printer. So once this is suspended, you can continue processing or computing this routine. So whenever printer becomes ready, okay, whenever the printer becomes ready, it would send a interrupt request signal. Okay. Now, whenever in response to the processor processor interrupts the execution of the compute routine, it would give the control to the print routine. Now the print routine, it gives the second output line to the printer. Once printer starts printing, your print routine would be suspended temporarily. Then again your compute routine can be executed. Now this process goes on till your all lines of output are executed or it has been printed. Now this print routine will be restarted whenever the next set of lines would be available for printing. If the compute routine takes longer time to generate the end lines than the required time to print them, the processor will be performing any useful computations all the time. Okay, now we will see how this works. The routine executed in response to an interrupt request is called the interrupt service routine, which is print routine in our case. So whenever this compute, we had considered example like a person 1 is doing some, he is talking continuously and person 2 comes and interrupts him. The same thing will apply here. Say suppose your compute routine is continuously performing the task and it is producing some output. Someone comes and interrupts this compute routine. Then once this interrupt occurs here, now this interrupt is sent by your printer saying that it is ready to take the next line of output. So whenever the interrupt occurs, this compute routine, it will stop its execution. Then whenever the interrupt occurs, its corresponding interrupt service routine would be executed. In our case, so print is our interrupt service routine. So your interrupts are somewhat similar to your subroutine calls. Assumption is that here, say suppose compute routine is computing something and say suppose interrupt occurs at this point at I. At instruction I, your interrupt occurs at this time. Whenever your compute routine is computing something, the printer says that it is ready to take except the next line. So what your compute routine would do is, it will complete the execution of the instruction I. Remember, it won't stop it in the middle. Even if it gets the interrupt request, what it would do is, it will complete the execution of this instruction. Then what will happen is, your program counter comes into picture. It loads the program counter with the address of the first instruction of the interrupt service routine. That means whenever this instruction is executed, okay, the I instruction has been executed and the interrupt occurred here, your control now must move on to here. That means your interrupt service routine has to be executed. So for example, or for easy understanding purpose, we will assume that this address, the first line of the first instruction or the address of this print routine is hardwired in the processor. That is, say example, the location is at J. Okay. Now after execution of the interrupt service routine, the processor has to come back to this compute routine and it has to start execution from this step I plus 1. So what would happen is, whenever a interrupt occurs, okay, whenever the interrupt occurs, so say suppose instruction I is executing in between, so that your PC, what will happen is, it would be pointing to your I plus 1. Okay, this is normal. And say suppose interrupt occurred in at this point at I, what will happen is, the contents of the PC, that is I plus 1, is put into a temporary storage in a known location. Now a return from this routine, interrupt service routine, a return from interrupt service routine, it reloads the PC from the temporary location to this I plus 1. In many processors, this return address is saved on the processor stack. Alternatively, it may be saved in a special location such as the register provided for this purpose. Getting it? How the interrupt occurs, and whenever the interrupt occurs, how it should jump to the interrupt service routine, then how it has to come back to the compute routine and the main routine, and then the execution should continue. Okay, that's it for today. We'll conclude our session. Thank you.